Next question. Does it matter how you write stuff? Because we're talking about, processes that reactions that have, where the forward version and the reverse version are happening simultaneously. So in that case, if both processes are happening simultaneously, are the reactants and products that defined, and does it matter which way we write it? And the answer is actually it kind of does, but merely just for the sake of convention. So let's look at this reaction right here. Hydrogen reacts with iodine to form 2 moles of hydroiodic acid, HI. Now I could ask you to write the equilibrium constant for this, and hopefully you would give me something that looks like this. So in terms of the concentration-based equilibrium, it's going to be the concentration of HI squared divided by the concentration of H to the first power divided by the concentration of I2 to the first power. I'm going to call this Kc1 because there will be other equilibrium constants on this slide. And it turns out that that's equal to 57 at a temperature of 700 kelvins. But we could just as easily have written it in the other way around, because remember, both processes are happening forward and reverse. So I could say, well, it's 2HI giving us a mole of H2 and a mole of I2. What would the equilibrium constant for this expression be? And what would, if it's different, what is its relation to this one that I called Kc1? So construct the equilibrium constant and tell me, if you think it's different, tell me what it is and what the relationship is. All right, so I'm going to call this Kc2, and it's going to be, again, products over reactants raised to the appropriate power. So I've got H2 to the first power, I2 to the first power, divided by the concentration of HI to the second power. And if you look at it, that happens to be the exact inverse of Kc1, which means that you can expect this numerical value to be 1 over 57, or 0.18. So there are 2 morals to this story. Number one, just because of the products over reactants convention, specify the reaction as you're using it so everyone knows what you are referring to as the products and what you are referring to as the reactants, because it does matter. And the other thing is that if you're looking at reversing reactions, the process is that you invert the value of K. This will come into play because we can play thermodynamic games with these equilibrium constants like we did in Hess's law. Or if you reversed a reaction, you flipped the sign on delta H, and if you doubled the reaction, you doubled delta H and stuff like that. So you can play that same game with these, but the rules are a little bit different. So rule number one is if you flip a reaction or reverse it, K doesn't get reversed, it gets inverted. How do you spot this problem? Equilibrium constants are always positive numbers. They might be very small, but they are always above 0. All right, so let's look at our Kc1 again. I alluded to what happened in thermodynamics when we halved a reaction or doubled a reaction. So let's play that same game with an equilibrium constant. So technically, this also is a balanced equation. 2 moles of H2 with 2 moles of I2 becoming 4 moles of HI. Now, it's not the way we would normally write it, but again, in playing in some thermodynamic games, in specifying reactions as the result of a series of reactions, you might want to look at it this way. So again, what I want you to think about is, what's the equilibrium constant for the equation if it's written this way, and what is its relation to that equilibrium constant? And remember, we've doubled these, and you should get HI to the 4th power divided by H2 squared divided by I2 squared. And that is not double, but the square of the expression for Kc1. So it's the square of this one. So that means numerically it would be equal to 3249, written this way. excuse me, again at 700 Kelvin. And again, make sure you specify it. And here the rule is that if you are multiplying reaction coefficients, you want to raise the equilibrium constant to that multiplicative power. So what does that mean? If you double the reaction like we did here, the reaction gets squared. If you reduce all the coefficients by 1/2, you end up with the square root of the previous equilibrium constant. If you triple everything, you cube the equilibrium constant. So whatever the multiplication factor is, you raise the equilibrium constant to that power.